Okay, let us continue with the electrochemistry. So we already discussed what is a conductance, specific conductance and specific resistance and so on. Now we will try to understand molar conductance. So it is designated by the symbol lambda m. This is a capital lambda. So it's called as a molar. Now the definitions of molar conductance is actually the conductivity power of all the ions produced when 1 gram molecular weight or 1 mole of the substance or electrolyte 1 mole of the electrolyte is dissolved in a given solution. So that we call it as a molar conductance. Now say for example, if you take NaCl, so the molecular weight of NaCl is actually, so this is 35.5, this is 23, so 58.5 gram. So if I dissolve 58.5 gram of NaCl, that is 1 mole in a given solutions of 1000 ml or 100 ml, whatever it may be, irrespective of the volume, then we will call now the conductivity power of all the ions produced. That is, if you dissolve this 58.5 gram of NaCl in a water, so it actually leads to Na plus and Cl minus. Now the conductivity of all the ions produced, now that we call as molar conductance. So in the case of NaOH, we need to take 40 gram. So 1 mole is actually 40 gram. Now the conductivity of Na plus and OH minus produced when 40 gram of NaOH is dissolved in a given amount of the solutions, that we call it as a molar conductance. Now there is a connections between molar conductance to the specific conductance. This molar conductance is actually irrespective of the volume. So if I take, but specific conductance is this is with respect to volume, that is the conductance produced by 1 cm cube of the solutions, then we call it as the specific conductance. Now if the 1 cm cube of the solutions contains, imagine 1 cm cube of the solution contains 40 gram of NaOH, that is 1 mole of the electrolyte. NaOH is an electrolyte. Then we call it as a molar conductance. Then we call it as the molar conductance is equal to, because 1 cm cube solution contains 40 gram. So therefore the molar conductance is equal to the specific conductance. Conductance is 1 cm cube of the solution. The conductivity power of all the ions that is present in 1 cm cube of the solution. So here the number of ions that is present in 1 cm cube of solution is equivalent to the 1 mole of the NaOH. That is 40 gram of the NaOH. Now we can call this lambda m is equal to K, kappa. That is specific conductance. Now we need to try to develop a relationship between the molar conductance and the specific conductance. The relationship between specific conductance and molar conductance. We'll take a two conducting plate. Now let us consider two conductivity plate. Now this is two conductivity plate. It's connected to a negative terminal which is connected to a positive terminal. Now the length of this conductivity plate, this two plate, is separated by 1 centimeter. Now the area of the cross section is will be 1 centimeter. So if you put an electrolytic solutions, the area of the cross sections will be 1 centimeter square. So now the total volume will be 1 cm cube of the solutions that is present in this container. 1 cm cube of the solutions. Now the conductance offered by the 1 cm cube of the solutions is nothing but specific conductance. Now suppose the same 1 cm cube of the solutions contains 1 mole of the electrolyte. 1 mole of the electrolyte. Now that the conductance offered by the same electrolytic solutions that contains 1 mole of the electrolyte will be equivalent to the molar conductance, because it contains 1 mole of the electrolyte, that is we call it as the molar conductance. Okay, now if it is diluted, now this, if it is contains 1 cm cube, now if I extend this solution, now what will happen? Now 1 cm cube of the solutions, 1 cm cube of the solutions contains 1 mole of the electrolyte. Mole of the electrolyte. So the 1 mole is actually, we can measure in terms of molarity. Correct? Now what is the definitions of molarity? So molarity is equal to number of moles that is dissolved in per liter of the solutions. Number of moles that is dissolved in per liter, the volume of the solutions, per liter of the solutions. Now we can take the volume, number of moles, molarity. Now in order to get molar conductance, we need to use 1 moles, that is number of moles is 1. Now this is actually the molarity. So the molarity, we can, it's a concentration. So it is a parameter to express the concentration. So what we can do, we can put a C. So this is molarity, 1 by C. Now this is B liter, this is 1 by C mole. Now if you carry out for the liter to ml, V ml, that is 1 liter contains 1000 ml. Now C into molarity. Okay. Now as well as volume. So if it is only 1 ml, if it is only 1 ml contains 1 mole of the solutions, 1 mole of the solutions is actually the molar conductance, and if it is 1 ml, we call it as a specific conductance. Call it as a specific conductance. Now the same 1 mole, it's not contained in 1 ml, but it is contains in 1000 ml. Now if it is contains in 1000 ml, that present 1 mole of the substance, still it is a 1 mole, so therefore we call it as a, still it is a molar conductance, but the volume is increased to 1000 times. 1 ml means we call it as a specific conductance, but 1000 ml means 1000 times the specific conductance, 1000 times the specific conductance. So the specific conductance of this will be so now the molar conductance will be lambda m. This is K. This is if it is 1 mole of the substance present in 1 cm cube of the solutions. 1 mole of the substance present in 1 cm cube of the solutions. If it is lambda m, if it is present in 1000 ml of the solutions, 1 mole actually present in 1000 ml of the solutions, then will be kappa into 1000 divided by C, where C is the concentration. C is the concentrations. Here K by C, just a K by C. Why? Because the 1 mole, so 1 cm cube of the solutions contains 1 mole of the substance. Here 1000 ml, 1 liter of the solution contains 1 mole of the substance. So here just 1 ml or 1 cm cube into 1, but here it is 1000 ml, it contains 1000 ml of the solutions contains same. So here also we call it as molar conductance, here also we call it as molar conductance, but here the molar conductance is directly equal to specific conductance because it is 1 ml, but here it's per liter 1000 ml, that is why we need to increase it by 1000. Now this is the formula in order to calculate the molar conductance. This is the formula in order to calculate the molar conductance is equal to kappa into 1000 divided by C, where C is molarity. Where C is the molarity of the solutions. Now unit of this molar conductance, unit of molar conductance. So then kappa is actually Simon meter inverse. This is concentration is actually mole inverse meter cube. So mole inverse per meter cube. So if you take the, so we can write like this in order to calculate. So this is Simon meter inverse, this is mole per meter cube. If you make it above Simon meter inverse mole inverse meter cube, meter inverse meter cube will cancel, we will get Simon meter square mole inverse. Now this is the SI unit of molar conductance. Now similarly another conductance, that is equivalent conductance. Equivalent conductance. So in case of molar conductance, the conductivity power of all the ions produced when 1 gram molecular weight or 1 mole of the electrolyte is dissolved. But in the case of equivalent conductance, we have to take 1 gram equivalent weight of the electrolyte dissolved. So it is the conductivity power of all the ions produced when 1 gram equivalent weight or equivalent weight of the electrolyte is dissolved in a given solution. So it's called as equivalent conductance. Now the relationship between the equivalent conductance can be represented as lambda EQ. We call it as equivalent conductance. The same. So if we take two conductivity plates, now here we have this electrolyte. Now it is separated by 1 centimeter. Area of cross sections will be 1 centimeter square. Now if it is now we call it as specific conductance, as long as it is specific to the length and area of the cross sections. Now the conductivity power of all the ions that is present in 1 cm cube of the solutions, we call it as kappa. So that is specific conductance. Now the same electrolyte, the same amount of the electrolyte contains one equivalent weight of the electrolyte. Now the electrolyte contains one equivalent weight of the electrolyte. Now we call it as now it contains one equivalent weight of the electrolyte, so therefore the conductance will be equivalent to the equivalent conductance because it contains equivalent weight of the electrolyte. The conductance is due to all the ions that is produced by 1 gram equivalent weight of the electrolyte. Equivalent conductance. Now the lambda EQ is equal to kappa divided by C. So because it is equivalent weight per meter cube or per centimeter cube, where C is the concentration of the electrolyte expressed in normality. In the molar conductance, the concentration of the electrolyte expressed in molarity, but here normality. So normality is equivalent weight per cm cube. Equivalent weight per cm cube. The number of equivalent weight per cm cube, we call it as normality. Now that is kappa. As long as it is with respect to cm cube, we call it as specific conductance. As long as it's equal to equivalent weight. Number of equivalent weight is equal to 1 gram equivalent weight. Now we call it as equivalent conductance. If it is same, now if it is 1000 ml, so K by C. Now if it is 1 cm cube, now the number of equivalent weight will be 1000 cm cube. Now the specific conductance will be increased by amount of 1000, so therefore it has to be multiplied by 1000. So this is normality. So this is the expression for the equivalent conductance, kappa into 1000 C, where C is the concentration of the equivalent weight that is expressed in normality. So this is, we call it as an equivalent conductance. Now the unit is same, but instead of mole we get equivalent, as Simon meter square equivalent inverse. So this is, we call it as the SI unit of equivalent conductance, unit of equivalent conductance. There is a problem with respect to the equivalent conductance. Calculate the equivalent conductance of a solution having a specific conductance 1.1 Simon meter inverse and whose concentration is 0.1 normal. Now with C is given 0.1 normal and specific conductance is given 1.1 Simon meter inverse. Now the equivalent conductance will be 1.1 into 1000 divided by 0.1. Now we will get the answer. So after calculating, we will get the answer as lambda EQ, that is equivalent conductance. Now we all know that the conductivity power of 1 cm cube of the solutions, we call it as specific conductance. Now if it is the same 1 cm cube of the solutions contains an equivalent weight of the electrolyte, then we call it as equivalent conductance. Okay, now if it is contains molecular weight, a gram molecular weight of the electrolyte, we call it as a molar conductance. Now suppose we are not going to change the weight. Suppose we are diluting with 10 ml. If you diluted the same amount of the electrolyte with 10 ml, so still it is an equivalent conductance or molar same, because it contains only the equivalent conductance is the conductivity power of all the ions uh, produced by 1 gram equivalent weight of the electrolyte or 1 gram molecular weight of the electrolyte. So if it is diluted, now that is also equivalent to the equivalent conductance. But so specific, if it is L, then K by into 10. Now if it is 100 ml, 1000, if it is 1000 ml, kappa into 1000. So still it is a equivalent conductance, but the specific conductance is multiplied by 1000 times the specific conductance. So now we are going to see the effect of dilution. So if you're diluting, so what is going to alter? So the first parameter is actually conductance. What happens to conductance? Now the conductance of a solution is due to the presence of ions in solutions. The conductance of a given solution is due to the number of ions that is present in the solutions. Since on dilutions, what will happen? The degree of dissolutions of the electrolyte is increased. The degree of dissolutions will be increased. So once the degree of dissolutions of the electrolyte is increased, and more ions will be produced, the number of ions will be increased. So once the number of ions is increased, more ions will be produced. Once more ions is produced, that is, it is expected that the conductance G is also increases. The conductance of the solutions also increases upon dilution. Say for example, so we have a container, we have 100 ml of water, say for example. Now it contains 1 gram of the solutions, 1 gram of any electrolyte, 1 gram of the NaCl per 100 ml. Okay, 1 gram of NaCl 100 ml. Now as the dilutions increased by 250 ml or 200 ml, now we are increased to same 1 gram of NaCl. Now it is 200 ml. As the dilutions is increased, now what will happen is that, so when 1 gram of NaCl is present in 100 ml, there is a chances that the Na plus and Cl minus are very close to each other. So because of the decrease in the volume, so because of the lower volume, there is a chances that Na plus and Cl minus will recombine. So because of the space provided by the 100 ml of the solution, so there is a lesser interaction, because the amount 100 ml, the interaction is constant. As we increase the amount of the solvent, now the interactions of solute interaction of solvent to solute increases. Okay, once increases, and the distance between the two ions, the distance between the two ions increases. So once the distance, because of the more amount of the solvent molecules we are going to add, the distance between the two ions increases. Once the two ions increases, there is a less chances to the recombinations, less chances of recombination, and there is the undissociated NaCl will undergo dissociations. There will be complete dissociations as the more amount of the solvent molecules is added. The undissociated will undergo dissociated as Na plus and Cl minus. Thereby the degree of dissociations will increases. The degree of dissociation. Once the degree of dissociations increases, automatically the conductance of the solutions increases. So this is the effect of dilution. So next is actually specific conductance. Now specific conductance is due to the number of ions that is present in 1 cm cube or 1 ml of the solutions, correct? 1 ml of the solution. How many ions are present in 1 ml? That conductance we call it as a specific conductance. Now upon increase in the dilutions, so say for example, so if you take there are 20 ions are there in 1 ml. Okay, now this is we call it as specific conductance, 20 ions. Now it is increased to 10 ml. Now the dilutions is increased to 10 ml, but the number of ions is only 20 ions are there in 10 ml. Now if 20 ions are there in 1 ml, we call it as specific conductance. Now the number of ions is same, the constant, but now increase the dilutions, increase the amount of water. Now what will happen is that the 20 ions is equally distributed in 10 ml. So the number of ions in 1 ml will be equal to 2 ions. Now if it's 1 ml 20 ions, now here 1 ml 2 ions, the number of ions is decreased per ml. Now what will happen upon dilution, the number of ions per ml decreases. Now the number of ions per ml is a specific conductance. So if the number of ions per ml decreases, means the specific conductance obviously decreases. Specific conductance is also decreased. So the conclusion is that upon dilutions the specific conductance is also decreases. Why? Because the number of ions per ml decreases. Another terminology, that is equivalent conductance. Another parameter upon dilutions is equivalent conductance. Now upon dilution the equivalent conductance increases. So how it is increases is nothing but the equivalent conductance is nothing but it is a product of specific conductance and volume. Okay, upon dilution the specific conductance is decreases, that we already stated. But how this equivalent conductance is also a product of specific conductance and volume increases? Because here the specific this actually decreases by an amount. The specific conductance itself is decreased by an amount will be which is compensated more by increase in the volume. If the specific conductance is decreases by an amount of x, if it is x, but the volume is increased by 100x, upon increasing the volume the specific conductance is decreases by an amount of, say for example, convenience, x amount is decreased, but by increasing the volume the total conductance increases by an amount of 100 times the x. So therefore, which is much more compensated the decrease in the specific conductance by increasing the value. That is why the lambda EQ, that is the equivalent conductance, increases upon dilutions, which is more compensated by increasing the volume. So this is how it will be increases by amount of 100 because of the increase in the degree of dissociations. Increase in the degree of dissociation. Increase in degree of dissociation, that will leads to more number of ions that contribute more to the conductance. That is why the equivalent conductance upon dilutions increases. Now molar conductance. So this is also a product of molar conductance. So this is also a product of kappa and volume. The C is constant, but upon increasing the volume, this volume increasing the volume, upon dilution increasing the volume, this decreases. Specific conductance decreases, but which is compensated by increasing the volume due to the degree of dissociation. The same explanations will be also here also. So the conclusion is upon dilution, the molar conductance increases. Upon dilution, the molar conductance increases.